what motivates people, what motivates Taylor to invent or to discover Taylor expansion or Taylor series. The possible motivation I'm going to discuss in this video. So why, in other words, why f of x as a function can be written if the nth order derivative exists at a point x naught. Why this function can be written as a series of sum of a series of polynomials plus a infinitely small amount, little omicron of x minus x naught to the power of n. Again, let's remind ourselves the meaning of little omicron. So basically, if you move this Taylor series, right, Tn over to the left-hand side, that means the difference between this function and this polynomial can be written as a infinitely small amount, right? So this is a notation which denotes a function in terms of x that approaches 0 very, very fast as x approaches x naught. How fast it approaches 0? Faster than the speed of x minus x naught to the power of n, faster than this infinitely small amount. That's what it means by little o of this amount. So first of all, let's start with a simple case. Let's observe if the first order derivative exists, what will happen? Right, so that means the f of x minus f of x naught over x minus x naught approaches f dash x naught. Right. So that's the meaning of derivative as x approaches x naught. Now, if we just move this term to the other side, to the left hand, we have f of x minus f of x naught. Common denominator is x minus x naught. Right? X minus x naught. Minus this, so this times the denominator, right? So minus f dash of x naught times x minus x naught approaches 0, because I've already moved this term to the other side, right? So this type becomes 0 as x approaches x naught. So this is what we observed. So remember the meaning of little omicron, right? So that means let's observe the denominator as x approaches x naught. This denominator already approaches 0. So that means, how about the numerator, right? As x approaches x naught. Because the first order derivative exists, therefore this function must be continuous at x naught, right? So that means the limit of fx as x approaches x naught has to be equal to the fx naught, right? So fx naught minus fx naught equals 0. And this approaches 0. This is just a constant. So top is still 0. So we have an infinitely small amount divided by an infinitely small amount still approaches 0. So the only possible explanation is that the top infinitely small amount is even smaller than the bottom infinitely small amount, which means the top infinitely small amount approaches 0 faster than the bottom, right? So that's what it means by little omicron. So that means the top quantity can be denoted as little omicron of x minus x naught, right? So in other words, we can just imagine if we just multiply this bottom over to the other side, right? Just treat 0 as a little omicron, whatever. Just imagine that. Right? That's one way of thinking it. F of x minus f of x naught minus f dash of x naught times x minus x naught can be denoted as little omicron of x minus x naught. And if we just move this term to the other side, now we have f of x can be written as f of x naught plus f dash of x naught times x minus x naught plus little omicron of x minus x naught. Right? This is already looking very much like our Taylor expansion already, except we don't have such a high degree. Right? So this motivates us to think, okay, now we've represented f of x, our function, as a constant, right? This is a constant, plus some constant multiplied by another polynomial, plus an infinitely small amount, which is even smaller than x minus x naught. Right? So this motivates us to think whether we can represent f of x in terms of a sum of a series of polynomials and plus some infinitely small amount that's even smaller than this one. How about x minus x naught to the power of 2, to the power of 3, to the power of n, as we have more polynomials participating in this series? How about that? Can we do that? That's our motivation. Right. So in other words, can we ask ourselves, can we rewrite f of x as the following? Some constant, right? A plus some other constant b times some polynomial, right? X minus x naught plus some other constant c times some other polynomial, x minus x naught to the power of 2. Right, that's our pattern, right? X minus x naught to the power of 1. Right, so this should be x to the power 2 plus some other constant d times x minus x naught quantity power of 3, and plus little omicron of x minus x naught to the power of 3. Right? So the reason we have this motivation is that we hope we can write our function as the following sum of a series of polynomial, is because we hope the benefit of doing this is that now, if this is true, now that means the difference between my function and this quantity as a polynomial can be written as a little omicron of this thing, which means the difference between this quantity and that quantity only differs by a very, very small amount, even smaller than x minus x naught to the power of 3, which is already small enough. So that means the higher degree we can expand it, the better it's going to be, because the more precise we can approximate our function with a little omicron of x minus x naught to the power of as high as possible, right? Because the higher the power is, the smaller this quantity is. So, which means the difference or the margin of error between this quantity and this quantity will be also small enough, which means we can approximate to our function as precise as possible. So that's from from physics point of view. So in other words, if it's true, can we find out the exact value of A, B, C, and D? I think so. Why? Just imagine. Let's let x approach x naught. What will happen? Right. When that happens, like I said, let's assume that the third order derivative at x naught exists. Right. That's our assumption. Then automatically, which means we can easily verify that since the third order derivative exists, therefore the first order derivative has to exist as well at x naught. Therefore, the function has to be continuous at x naught, which means as x approaches x naught, f of x has to approach f of x naught. Right? So left-hand side we have f of x naught. On the right-hand side, still a, just a constant. And this approaches that, means this quantity approaches 0. 0 times the constant, still 0. And this, likewise, 0 times c, still 0. This, still 0. 0 times d, still 0. How about this? 0. Even smaller than this infinitely small amount. Of course, even more 0. So that means A should exactly equal to f of x naught. All right, that's our result. So which means we've solved A successfully. Is the functional value at exactly x naught. And likewise, we can continue to solve for B. Right? If we just, this time we'll do something different. This time let's divide everything by x minus x naught. Right? Because otherwise B will just disappear as we let x approaches x naught. Right? We need to get rid of this thing, right? By dividing by it. So that means on the left-hand side, now I have f of x. Let's also move a to the left-hand side, right? Minus a. Minus a is this one, right? F of x naught. Then we divide everything by x minus x naught. Right, so on the right-hand side, there's no more a. And this divided by x minus x naught, we're only left with b. Next term is, I'm left with c times bracket x minus x naught plus d times x minus x naught quantity to the power of 2 plus little omicron of x minus x naught quantity to the power of 2. The reason we can straight away divide the little omicron of x minus x naught to the power 3 divide by x minus x naught and rewrite it like this, it's legal because it's easily verifiable. The reason is because okay, let's just quickly. So in other words, we want to show that if we want to show that little omicron of x minus x naught to the power of 3 after divided by x minus x naught, can it be written as little omicron of x minus x naught to the power of 2, just like doing normal division, right? Normal division. Can we actually do that? The answer is yes. All we have to show that if it's true, that means the little omicron of this thing means if this quantity divided by this thing is still infinitely small, right? So is this thing divided by this term still infinitely small? In other words, is this thing divided by this amount still infinitely small, right? X minus x naught to the power of 2, right? So to the power of 3. That's after we, right? Previously I have x minus x naught, then I have to divide it by x minus x naught to the power of 2, then I have x minus x naught to the power of 3. Can this quantity still be infinitely small? Infinitely small? As x approaches x naught? Yes. Why? Because the meaning of little omicron of this x minus x naught to the power of 3 is exactly means after divided by the same quantity, it is infinitely small. Right? So really it's true. So indeed we can just like doing normal division, right? Can be written like this really. Now we can do the same process. We can let x approaches x naught. What will happen? Right, likewise here. So the meaning of, remember, left-hand side, what does it mean? It means if the meaning of derivative, first order derivative, right? Because I assume the third order derivative exists, it must mean that the first order derivative, of course, exists, right? So left-hand side, I have x dash of x naught. That's the first order derivative of x at the point x naught equals right-hand side. What do I have? B, right? Still a constant. This one, right? As x approaches x naught, this term approaches 0. So is this term. So is this term, right? Easily, they all approach 0. So that means b is equal to the first order derivative at x naught. So I've solved for b. Likewise, I can solve for c. Okay, coming back to our result, I've just established that the a should exactly to f of x naught, b should equal to f dash of x naught. And following this expression, series polynomial, and assuming the third order derivative exists at x naught. And now we're going to try to find out the value of c and d. So likewise, again, if we just straight away let x approaches x naught, it will be meaningless because c will automatically disappear. Right? So likewise, we're going to try to move this term onto the left-hand side and divide everything by x minus x naught to the power of 2. Therefore, we can isolate c. Right? So f of x minus a is known to be f of x naught minus b times x minus x naught. B is known to be f dash x naught. Right? F dash x naught times x minus x naught. Right? Right, so this minus divide everything by x minus x naught to the power of 2. X minus x naught to the power of 2. And what do we have on the right hand side? We have c, right, which is isolated, plus d times, after divide by this term, we have d times x minus x naught, plus little omicron of that divided by x minus, like I said, we can do normal division, just like normal algebra. Right, plus little omicron of x minus x naught. Now we can let x approaches x naught, because c still remains. That's the benefit. So on the left-hand side, what do we have? Seems like an undetermined form, 0 over 0, right? The bottom, we have something that's approaching 0. On the top, we have, like I said, as x approaches x naught, is easily verifiable that from our assumption, f of x is continuous at x naught. Therefore, the limit of as x approaches x naught of fx should exactly equal to f of x naught. Therefore, they just cancel out. And we're left with this one. This one approaches 0, right? So 0 minus 0. So still 0 on the top, 0 over 0, undetermined form. And we can use L'Hopital's rule, right? To find out the limit of this, we just have to differentiate both top and bottom, then operate from there, right? So differentiate this one, f dash x. This is a constant, gone. This is a constant times x minus x naught, right? So this automatically becomes minus f dash of x naught, right? Constant. And on the bottom we have chain rule, 2 times x minus x naught. So what's the pattern here? What do we have here? F dash x minus f dash of x naught. We can treat f dash of x as another function, right? It's a derivative function, also a function. Right, so a function minus the function at functional value at x naught over twice of x minus x naught. That's exactly the definition of the derivative of function f dash x at x naught. What's the derivative of that? That's easily, we'll copy down a 2 here. So 2 factorial, right? Same thing. So f of double dash x naught, right? That's the second order derivative at x naught, right? Can be easily seen. The pattern is become more and more clear. So that's the on our left-hand side, our limit seems to be this one, right? How about right-hand side? What do we have? C remains C, right? And this approaches 0, obviously, right? As x approaches x naught. This also approaches 0 easily. So therefore, C should equal to this one, right? So we found out C. 2 factorial f double dash of x naught. And we would assume that we hope D would be equal to 3 factorial and f third order derivative of x naught. That's what we hope. But let's find out, right? Likewise, let's move this term, all to the left-hand side. Right? So f of x minus a. A is known to be f of x naught minus b times minus this term. This term is easily f dash of x naught times x minus x naught. This term, right? This term minus 2 factorial f double dash of x naught times x minus x naught to the power of 2, right? And we divide everything by x minus x naught to the power of 3. That's on the left-hand side. And on the right-hand side, this, and this are gone. And this divided by this is what? Just D. And this divided by this is just little omicron of just 1. Little omicron of 1 just easily approaches 0, right? Because what does it mean? It means this quantity divided by 1 approaches 0 as x approaches x naught. So this is infinitely small. Don't worry about that. And we just need to find out the value of D, right? Likewise, we let x approaches x naught. Find out the limit of the left-hand side, right? So on the bottom, it's still 0, right? Approaches 0. On the top, what is it? So x approaches x naught, fx approaches f of x naught minus f, this and this cancel out. And this approaches 0, this constant still 0, and this approaches 0, constant still approaches 0. So 0 over 0, undetermined form. Using L'Hopital's rule, we have first differentiate top, we have f dash of, so f dash of x, the constant term gone, constant term times this term, so minus f dash of x naught. And this is also a constant term, chain rule, 2 times that, 2 and 2 cancel out, we have minus f double dash of x naught times x minus x naught. And differentiate the bottom. 3 times x minus x naught to the power of 2. Right? And now it's still an undetermined form. Right? Bottom still approaches 0, top as f x approaches x naught, f dash of x approaches f dash of x naught, because f dash of x as a function is continuous at x naught. Why? Because the existence of the third order derivative at x naught indicates implies the existence of the first order implies the second order derivative exists at x naught, which implies the existence of the first order derivative nearby x naught. Right? X is nearby x naught. Right? It's easily verifiable. And so this approach is f dash of x naught. So this and that cancel out. And this easily approaches 0. So still 0 over 0 undetermined form. And it's differentiate again. Right. So it becomes f double dash. F double dash of x minus a constant term, right? This fixed x naught, constant term gone. Say, so minus f dash. Minus f double dash of x naught. That's a constant times this polynomial, right? Easily. Differentiate the bottom, right? So 3 times 2. 3 times 2 is just 3 factorial, right? Using chain rule, we have x minus x naught. Now we let x approaches x naught, see what the limit of this is. So this is easily the very definition of the derivative of the function of f double dash of x as a function in its own right at the point x naught. Right? We have to copy down this constant as well. So that's exactly 3 factorial at the top, bottom, top. That is f third order, right? Because I'm treating f double dash of x as a function in its own right. So that's the f of third order derivative at the point x naught. So the pattern is very clear. So this is in the end the limit of left hand side, right? Right hand side is easily approach d, right? So d is easily this thing, right? So the third order derivative at x naught over 3 factorial, easily. I've just proven that f of x if can be written as the following expression, then a, b, c, and d have to be the following exact values. But I haven't proven that whether the difference between this quantity and that quantity is really little omicron of x minus x naught to the power of 3 if a, b, c, d are equal to those values. But they're easily verifiable after we just move all of these terms to the other side and divide everything by x minus x naught to the power of 3. Then we use L'Hopital's rule repetitively, probably 3 times, and then we can easily verify that their difference is really little omicron of x minus x naught to the power of 3. Easily verifiable. Now, pattern is very nice and clear. Right? Just the bottom is 0 factorial, that is 1. 1 factorial, 2 factorial, 3 factorial. At the top we have the f of x naught, that is the 0th order derivative, which is the function itself at the point x naught. First order derivative, second order derivative, third order derivative. Nice pattern, right? To our polynomial, that's x minus x naught to the power of 1, to the power of 2, to the power of 3. Right? In the end, we have a Peano remainder, right? So this is called Peano. So Peano remainder. So this motivates us to the following Taylor expansion. So now I've proven that the Taylor expansion theorem is really true when n equals 3, can really be written as a series of polynomials of degree of 3 plus little omicron of x minus x naught to the power of 3. So this motivates us to make the conjecture that can a function be written as a Taylor polynomial of degree of n plus little omicron of x minus x naught to the power of n being any positive integer. That's our conjecture. as long as we assume that the nth order derivative exists at x naught. That's our assumption. Under this assumption, is this Taylor expansion theorem true? So that's our motivation. I'll prove that in a future video rigorously.